following up on the last video, we're going to look at limit laws, some initial limit laws to get us going to help us compute more limits. What are these laws that tell the limits what to do? Let's take a look. So what we're going to do, these initial limit laws, is first of all we need to set up certain things that need to be true before we talk about the particular laws. And that is, we're going to assume that we have two functions, f of x and g of x. And both of these functions have limits that exist as x goes to a. So right here, limit is x goes to a of f of x, and limit is x goes to a of g of x. Both of them exist. We're also going to let the number c be a real number. So remember what that means. C is a real number. Okay. So we got a real constant. Got f of x and g of x have limits that exist as x goes to a. And then n and m are natural numbers. So that symbol n there, the set of natural numbers, remember, n and m are natural numbers. Just meaning that those numbers are the counting numbers, 1, 2, 3, 4, 5, so on and so on, positive whole numbers. So that's set up. So when we make a statement that we're about to make, it's important to note that we need these things to be true before we say anything else. Okay, so limit is x goes to a of f of x and limit x goes to a of g of x both need to exist. It's very important. C is some real constant, n and m are natural numbers, but most importantly, limits of x goes to a of f of x and g of x both have to exist. Okay? If that's not true, we can't say none of this stuff. But assuming it's true, then we have many different statements we're about to look at. Now the first one is this statement, which is called the sum law, S-U-M. And that is, if I take the limit as x goes to some real number a, f of x plus g of x, the limit of a sum of functions, then that is the same, at least claiming, that it's the same as the sum of the limits. And that is, limit of the sum of f of x plus g of x is the same as the sum of the limits x goes to a of f of x plus limit x goes to a of g of x. Now, even though we're not going to prove these statements in this video, and those proofs, by the way, entail something which is called epsilon delta proofs, and they can be proven. You can be assured these are all true. We're not going to do it in this video, but we're going to assume they're all true because we can do it. But for this first one, I want to show you kind of a graphical analysis of why it could be true, visual representation, and then you can kind of get the idea with the rest of the limit laws that I'm about to show you. You could do a similar thing graphically to kind of reassure yourself, but of course you could also prove it. So let's think about that. Got two functions. Just think of one function here. Square root function, y square root x. Let's pretend this is like our f of x, okay? And look at the picture there. We are investigating the limit as x approaches 1. So we can see in the graph, limit as x goes to 1 of the square root x is 1. So that's like, okay, we have a limit that exists at a particular location. Limit as x goes to 1 of the function square root x is 1. It exists. Boom. Check. Consider another function. Say y is x squared. We can consider this to be like g of x, some other function. And we're also looking at the same location here. Limit as x goes to 1 of x squared seems to be 1, right? I mean, seems reasonable based on the graph. So you basically have, in this first setup here, limit of one function, square root x, as x goes to the particular location 1, right? It happens to be 1. And you got another function, limit is x goes to 1 of x squared, some other function g of x, is also 1. And it's important to note x is approaching the same location, right? That's all true. What we need for these limit statements, x is approaching the same location for two different functions, and both those limits exist. Now, what if we add them up? If we add them up, we would get this function x squared plus square root x. So this is like your f of x plus g of x here. Right? You're talking about, what's up with that limit? As x goes to the same location, in this case 1. Then, at least as we can see graphically, sure seems to be that limit x goes to 1 of x squared plus square root x seems to be 2, based on the graph, right? And notice that, of course, that's 1 plus 1, but more importantly, that's same as limit x goes to 1 of square root x plus limit x goes to 1 of x squared. So it seems to be true, right? Like, limit of a sum of functions is the sum of the limits of the functions, assuming that each of the individual limits exists for each function. And so, this is really a conversation about combining functions or performing some type of function operation on a function. And when we do that, if the original limit exists, then these new limits also exist, assuming that the individual limits exist in the first place. So I just wanted to show you kind of that first law to say, you know what, again, we're not proving it, but it can be proven. And we can verify it and feel a little bit assured graphically that this is true. So you could do this on your own if you get a chance. So you can imagine the same thing would be true if I took the limit as x goes to some number a of the difference of two functions, f of x minus g of x. That's the difference of the limits. Limit is x goes to a of f of x minus limit x goes to a of g of x. How about if I take a function, f of x, and I multiply it by a real number constant? Remember, see here, some real number. Then what that's saying is if I multiply a function by a constant, that's a real number, and I take limit as x goes to a of that, that's just the same as taking the limit as x goes to a of the function times that constant. Again, can be verified in alternate ways. Same thing applies to when you multiply functions. Product law. If I take limit as x goes to a of the product of two functions, f of x times g of x, same as the product of the limits. Limit as x goes to a of f of x times the limit x goes to a g of x. On and on. Quotient law. If I take the limit as x goes to a of the quotient of two functions, f of x divided by g of x, that's the same thing as the quotient of the limits, and that is the quotient is limit as x goes to a of f of x divided by limit x goes to a of g of x. Now I gotta be a little careful here, because that's assuming that the limit as x goes to a of g of x is non-zero, right? Because if that were to happen, we'd have division by 0, and that's not gonna play the same game here. That's different games. So just take note, the function itself, g, could actually be equal to 0 at a, provided it's not the same as the value of this limit. So all we care about here is the limit as x goes to a of g of x being non-zero. Assuming that's true, then this law is also true. We got a couple power laws too before we look at an example here in a moment. Power law for whole number powers. So again, n is 1, 2, 3, 4, so on. If you take the limit as x goes to a of the power of f of x, the nth power, remember this notation here just means take the function and raise it to the power n, assuming n is not equal to -1, because then that would be an inverse function situation. Then if I take the limit of a power of a function, a whole number power, then that's the same thing as taking the limit as x goes to a of f of x, that limit itself, the one that exists in the first place, and raising it to the power n. And then finally, before we look at an example, fractional power law. Here we're going to assume positive fractions, so 3/4, 2/3, 4/13, etc. Take a limit as x goes to a of the function f of x raised to the fractional power n divided by m. And that is the same as taking the individual limit that already exists in the first place, limit as x goes to a of f of x, and raising it to the n over m power. And in this case, just to make it a little more general, and we can get real specific about this, but just to make this general case, we're going to assume that the function f of x is non-negative when the denominator m is even. So that's just to avoid like dealing with even roots of negative output values, and that's the whole complex number conversation. We're not dealing with that in this video. We're dealing with real numbers only. So again, these are some initial rules, laws, that we can say these things are established, they're true, they can be proven mathematically. And if you don't believe it, go play other games. Play games graphically, algebraically, whatever, and see that it works, assuming the limits exist in the first place. And they're going to allow us to do more things. So let's just take a little quick look at an example before we wrap up this video. And then we'll move on. In this example, we got three different functions: f of x, g of x, and h of x. And all of them were investigating the limit as x goes to 3. But that's important because the x location is approaching the same location for all of these three limits. Now, limit as x goes to 3 of f of x is 9. Just going to assume that. Limit as x goes to 3 of g of x is 2. And limit as x goes to 3 of h of x is 10. So important thing here to note, all three limits exist as x goes to 3 in the first place. And that's real important, right? Because all the limit laws are based, at least in part, that limits exist to begin with individually. And that's happening here. So given that that's the case, we're going to apply our appropriate limit laws when applicable to find some limits. So we've got different combinations of functions here. First one, we have limit as x goes to 3 of the quotient g of x minus h of x over f of x. Well, that is a combination of different rules, right? That is difference rule and quotient rule combined. Because really, if we wanted, we could write this as the limit as x goes to 3, g of x over f of x, minus limit x goes to 3, h of x over f of x. Because the limits individually exist in the first place as x goes to 3, and I know f of x does not have a limit as x goes to 3, which is 0. Which then allows me to write this as limit as x goes to 3 of g of x divided by limit x goes to 3 f of x. So in the first step, right, we're splitting up the difference of the different ratios. And now the difference of the ratios also have quotients in each of them, so I'm splitting up in the quotients using my limit laws. And then from this amount, we're going to subtract limit x goes to 3 of h of x over the limit as x goes to 3 of f of x. So you see, we break down a limit of stuff is the stuff of the limits, assuming the limits exist in the first place and all the conditions are satisfied. And now I can just go ahead and replace each of these limits individually by their numerical values as assumed in the example. So limit as x goes to 3 of g of x is 2. Limit as x goes to 3 of f of x, 9. Subtract from that. Limit x goes to 3 of h of x, 10. Over limit as x goes to 3 of f of x is 9. 2 ninths minus 10 ninths is negative 8 ninths. Bam. So we applied the limit laws appropriately and applicably to come up with this limit. Let's go ahead and finish off. Let's find the rest of these limits. How about limit x goes to 3 of 5 times f of x times h of x minus g of x? Here, product, difference, and then also constant multiplier. So we'll apply our rules. Again, in this case, it's going to be limit x goes to 3, f of x times 5 times h of x minus limit x goes to 3, g of x. So right there I did my difference law, split it up into difference. But then I got a constant times product. So product and constant. Oop. So this is going to be limit x goes to 3. And then while I'm at it, why not just take out the constant? 5. It's common multiplier. Constant multiplier. 5 times limit x goes to 3 f of x times limit x goes to 3 h of x. And of course minus limit x goes to 3 g of x. And now we can input the values as assumed. This is 5 times limit x goes to 3 of fx, that's 9, times limit x goes to 3 of h of x, that's 2, minus limit x goes to 3 of h of x is 10. And then minus limit x goes to 3 of g of x is 2. So what do we got here? That's 45 times 10 is 450. Minus 2, what do we get? 448. Bam. Limit laws at use. 2 more to go. And then guess what? That's the end of the video. Let's just do a couple more parts, parts C and D, and then we'll be on our way. In part C, limit is x goes to 3 of g of x squared. So it's that power rule where the power of the function, positive whole number. So according to the laws, this should be the same as limit x goes to 3 of g of x, and take that entire limit and here raise to the power of 2 or square it. Again, it's because we already know the limit is x goes to 3 of g of x exists. What is that limit? It's 2. 2 squared, 4. Bam. Finally, part D. Limit is x goes to 3 of fx quantity to the 3/2 power plus constant 1 on the outside. So fractional power here, right? And that power is a positive fractional power, so all's good. We also have a sum, right? So we can split this into a power and a sum as follows. This should be the limit as x goes to 3 of f of x quantity to the power of 3/2. Limit of a function to a power is the limit of the function quantity to the power. And then plus limit x goes to 3 of just the number 1. Now, we haven't talked about that just limit of a constant yet, but we'll think about it here in a moment. Now, here is the case where we go ahead and evaluate the fractional power part. As we know limit x goes to 3 of fx exists. What is it? It's 9. We're going to raise that to the 3/2. And the question is, what's going on here with limits x goes to 3 of 1? Now, we're going to see this in a video or two from now, is that y equal to 1 is technically a constant function. And moreover, it's actually a polynomial function. All right, let me write this a little bit closer. So if I draw that, here's the function, y is 1, it's constant. It's always 1 for every real number x. So if I go to 3 and I ask myself, what's the limit? Well, the function is defined for all real numbers, x, and it's always output of 1. So as we're going to see, limit is x goes to some number, whatever it is, in this case 3, of a constant function. It's just a constant. It's just always that number. And hence, 9 to the 3/2 plus 1 is what we get. Now, 9 to the 3/2 is, of course, square root of 9 cubed. Square root of 9 is 3. Cubed is 27. Plus 1, 28. So, there's just a couple of examples of the limit laws that we talked about at the beginning of this video. And we can always use those laws. So eventually we're going to get quick at it and just kind of bypass stuff. But first things first, we have to establish the laws. And we have to kind of show how they can be used. And as we get better, we'll be quicker with our computations. So that's it. That's Math and Beats, baby. And we're going to look at more limits. That's what this playlist is, limits and continuity. So lots more to say still about limits. And hope that helps you just establishing some limit laws and seeing how they could be used initially before we do some other things. Until next time, Math and Beats. Later.